In October 2017, a telescope in Hawaii detected something that should not exist in our solar system. An object moving so fast that the sun's gravity could not hold it. Within weeks, astronomers realized they were watching the first confirmed visitor from another star system pass through our cosmic neighborhood. They named it Oumuamua, Hawaiian for scout or messenger, and expected it to behave like a comet or an asteroid. Instead, it accelerated away from the sun without any visible mechanism to explain the push. That single anomaly turned a routine discovery into one of the most debated observations in modern planetary science. Oumuamua entered our solar system from the direction of the constellation Lyra, traveling at roughly 26 kilometers per second relative to the Sun. At that speed, it crossed the distance from Earth to the Moon in about 4 hours. The Pan-star's 20. One telescope on Haleakala detected the object on October 19, 2017, when it was already past its closest approach to the Sun and heading back toward interstellar space. Astronomers had only weeks to gather data before it faded beyond the reach of Earth's most powerful instruments. That narrow window shaped everything that followed. The measurements were real, but the object was already leaving before researchers could fully understand what they were seeing. Every observation became a race against the object's departure. Every telescope allocation, a gamble on which question would matter most when the data was finally analyzed. Those observations revealed an object unlike anything previously catalogued. Oumuamua's brightness changed dramatically as it tumbled through space, varying by a factor of 10 across a single rotation period. That variation suggested an extremely elongated shape, roughly 400 meters long and only 40 meters wide, a length-to-width ratio with no close parallel among known solar system bodies. Its surface appeared reddish, similar to objects in the outer solar system that have been exposed to cosmic radiation for millions or billions of years. The color confirmed long exposure to the interstellar environment, but told astronomers nothing about which star system had ejected it, or how long ago. The object carried no signature of origin, only evidence of time spent crossing the void between stars. The visitor behaved as expected, until astronomers analyzed its trajectory with precision. As Oumuamua sped away from the Sun, it accelerated slightly, moving faster than gravity alone could explain. When comets accelerate, they release jets of gas and dust as sunlight heats their icy surfaces, creating visible tails and measurable thrust. Oumuamua showed no tail, no coma, and no detectable outgassing in any wavelength astronomers examined. The Spitzer Space Telescope searched for heat signatures consistent with cometary activity and found nothing above the instrument's noise floor. The object was accelerating, but the mechanism was invisible. That contradiction between motion and observable cause became the central mystery that no single observation could resolve. Multiple observatories tracked Oumuamua's path as it left the inner solar system. The European Space Agency's optical ground station in Tenerife, the Gemini Observatory in Hawaii, and the Very Large Telescope in Chile all contributed astrometric measurements. Data from these facilities allowed researchers to calculate the non-gravitational acceleration with confidence. Published analyses in 2018 confirmed the anomaly. The object was being pushed by something that produced no observable exhaust, no measurable heat signature, and no debris cloud. The finding was not controversial in itself. What remained deeply contested was what could possibly explain it. Every instrument faced real limits. Oumuamua was small, distant, and moving fast, which meant astronomers captured only dim reflected sunlight across a compressed observation window. spectroscopic data was too weak to identify surface composition with certainty. No spacecraft was in position to intercept the object or photograph it at close range. Researchers could measure trajectory and brightness variations, but they could not resolve the object's shape directly, only infer structure from the way its reflected light fluctuated. The non-gravitational acceleration was real and statistically significant, but it was too small to detect in real time, emerging only after months of careful orbital analysis. The gap between what was measured and what could be explained was not a failure of instruments. It was a consequence of having almost no time. The object revealed itself only when it was already leaving, and every question answered opened two more that required observations no longer possible. Competing explanations emerged as researchers tried to reconcile the observations. One hypothesis proposed that Oumuamua was a comet with a composition that produced outgassing too faint to detect, perhaps releasing pure molecular hydrogen that would be transparent to most telescopes. A 2023 study formalized this model, showing that hydrogen outgassing from a porous, icy interior could reproduce the observed acceleration while remaining below Spitzer's detection threshold. A separate proposal suggested the object was a fragment of a larger body, tumbling in a way that created asymmetric radiation pressure. Some researchers explored whether it could be a thin, sail-like natural structure that caught solar photon momentum and converted it into thrust. No single explanation fit all the data without requiring assumptions about internal properties that could not be observed directly. The most widely supported explanation treats Oumuamua as an interstellar comet, with properties outside the range of objects formed around our Sun. Comets in our solar system release water vapor, carbon dioxide, and other volatiles when heated, creating visible activity. If Oumuamua formed in a colder or chemically distinct environment around another star, it might carry volatile compounds that produce thrust without generating a coma detectable at the distances involved. The hydrogen outgassing model does not require abandoning known physics, and it does not require invoking technology. It does require Oumuamua to have an unusual internal structure or composition, one produced by a planetary formation environment very different from our own. That possibility is scientifically uncomfortable only because we have no other interstellar object to compare it against. It is not implausible. Definitive answers will require better data from the next interstellar visitor. Astronomers estimate that several objects of similar size pass through the inner solar system each year, but most go undetected because current surveys do not cover the entire sky continuously, and because small, dark, fast-moving objects are easy to miss until they are already departing. Detection systems are improving. The Vera Rubin Observatory, designed to scan the full visible sky every few nights, will catch fainter and faster-moving objects earlier in their approach. Earlier detection means more time to study a visitor, gather spectroscopic data, and potentially coordinate a rapid response mission to fly alongside it before it exits the solar system. If the next interstellar object shows similar acceleration without any sign of outgassing, the anomaly deepens. If it behaves like a normal comet, Oumuamua becomes an outlier that challenges models of planetary formation around other stars rather than a signal of something entirely new. Either outcome changes what we think we know. Oumuamua forced astronomers to confront how little we understand about objects formed in other stellar systems. For decades, every comet and asteroid available for study was born around our Sun, shaped by our solar system's specific chemistry and orbital dynamics. The first interstellar visitor revealed that nature produces structures and behaviors that existing models did not predict. Its acceleration remains unexplained at the level of direct observation, not because the physics is impossible, but because the data was insufficient to distinguish between mechanisms that are each individually plausible. The object is now far beyond the reach of any telescope, carrying into interstellar space whatever answers we did not have time to extract. What Oumuamua leaves behind is a revised understanding of the problem. Objects from other star systems pass through our neighborhood constantly, shaped by formation environments we have never studied, composed of materials we cannot yet sample. We happened to notice one of them just as it was leaving. The question it posed, how an object accelerates without any visible cause, may be answered the next time one arrives, if our instruments are ready and our detection time is sufficient. Until then, the first messenger from another star remains exactly what it was when it was discovered. An observation that fits no clean category, and a reminder that the universe is under no obligation to match our expectations.